Okay, so yeah, thanks to the organizers for setting up this great event, and thanks also for the opportunity to speak. Um, so the outline of the talk is something as follows. So kind of the first half of the talk, we'll talk about some slightly older work that's joint with Zach Hamaker and Brendan Pawlowski from a couple of years ago, and then the second half of the talk will focus on some more recent constructions with Travis Scrimshaw. Um, Roughly, there's kind of three parts. So first, I want to talk about, Schubert polynomials, both in the classical sense, and then some, analogs for orbit closures in the type A flag variety. And then I want to motivate how certain product formulas for these dominant Schubert polynomials suggests the definition of key polynomials in the classical sense and some new definitions for shifted key polynomials. And then we'll talk about some formulas, positivity results, and conjectures. So I thought this might be a good audience to discuss these constructions with, because the most recent joint work with Travis kind of ended with a lot of conjectures that we weren't able to prove as much as we would hope. So I think maybe people from this audience might take away some of these definitions and maybe might see ways to prove some of the conjectures that we're observing. So throughout the talk, we're gonna work kind of simultaneously with three different families of permutations. So S infinity is just going to be the group of all permutations of the positive integers with finite support. So permutations that fix all but finitely many points. But we'll view these as maps from the positive integers to themselves. And then within S infinity, there is this subset of involutions, which are just the self-inverse permutations. So permutation is equal to its inverse precisely when all of its cycles have length 1 or 2. So you can think of elements of I infinity as just kind of incomplete matchings on the positive integers. And then we have a third set, which is morally just the set of fixed point free involutions in I infinity. But slightly technical distinction, we're going to think of this third set as just the S infinity conjugacy class of this infinite product of two cycles. So in some technical sense, this third set is disjoint from the first two, since it's not a finitely supported permutation, but it's just sort of just convenient to have all those this sort of infinite trailing two cycles, so that we don't have to worry about kind of running out of cycles on one end. So we have these three families of permutations. Each of them have kind of are infinite, but they have a natural kind of finite subsets within a particular symmetric group, which we'll talk about in a little bit. So let Si just be your usual simple transposition, swapping I and I plus 1, and then these guys generate S infinity. And then we're going to consider three different weak order graphs on these sets. So the first weak order is straightforward and familiar. This is just the usual right weak order on S infinity. So we have vertices which are elements of S infinity, and then we have an edge labeled by I from W to W times Si if I is an ascent of W. Then on this set of fixed point free involutions, we have a highly analogous graph structure. We draw an arrow labeled by I from W to W conjugated by Si if I is an ascent. So this is a multiplication is not going to preserve these fixed point free involutions, but conjugation will. So we just use conjugation instead of right multiplication. Now on I infinity, we do something a little bit more subtle. So there's two different kinds of edges from between elements of I infinity. So the edges are again labeled by ascents of your starting permutation W, which is an involution. But if you have an involution and you have a simple generator, there's two possible ways you could make a longer involution. So one is by conjugating, and then one is by multiplying in the event that your simple transition commutes with W. So we draw an arrow in these two different cases. The one final subtlety is that in the case when we are just multiplying, and so we're in fact increasing the number of 2 cycles in our involution, we're going to draw 2 edges instead of 1, or you could think of it as just a kind of a different colored edge. So I have some pictures of kind of some finite subsets of these directed graphs, just to give you a sense of what they look like briefly. So on the far left, we have the weak order graph on S infinity, but this is just on the finite subset of permutations of 1, 2, 3, 4. And you know, this is a nice graph. It's a, you know, lattice and other nice properties. But we see these other 2 weak order graphs on involutions are again graded directed graphs, but they're not necessarily lattices. And we see these red edges on the far right are the kind of doubled edges when you're increasing the number of cycles. Okay, so where do these let me tell you briefly just where these weak order graphs come from and how you might generalize them. So just fix a positive integer n and consider the set 1, 2, 3 up to n. And then we can consider these finite subsets, Sn, In, and INFPF, which are just the permutations that are preserving the complements of 1 up to n. So you'll notice that the fixed point free set is going to be empty unless n is even. So generally throughout this talk, whenever we're talking about sort of fixed point free involutions of an Sn, where n is always implicitly even. So if you take G to be just a general linear group over the complex numbers, and B its subgroup of lower triangular matrices, so it's Borel's subgroup, then there are bijections between these different sets of double cosets. So BB double cosets are in bijection with the symmetric group Sn. So this is just a standard Bruhat decomposition, or you can think about it as just doing a kind of Gaussian elimination on matrices where you're not allowed to swap rows, and then you'll end up with a permutation matrix. And then if you take the double cosets of the Borel subgroup B and either the orthogonal group or the symplectic group when n is even, you have double cosets that are in bijection with involutions or fixed point free involutions. Now, if you, you know, so in the B case, the BB double coset case, in fact, the correspondence between double cosets and permutations is straightforward. You're just putting W in between 2 copies of B. So in the orthogonal and symplectic cases, it's not quite literally true that when the KWB double coset corresponds to W, but there's some essentially kind of like square root of W that you want to insert in these cosets. So you have some correspondence between double cosets and involutions, and then these edges in weak order are corresponding to these closure relations where you're taking the closure of a double coset and you're multiplying it by B times SI times B, and that closure should be equal to another double coset. And so if you fix these indexing sets in a consistent way, then this will determine this weak order graph structure. Now, this number of edges business that we saw only in the sort of involution case corresponds to the degree of a certain map projecting from the G mod B to G quotient by a parabolic subgroup. So in general, there's some consistent way of defining these multiple edges. And you can make a similar construction and to get a kind of weak order graph on double cosets whenever K is a fixed point subgroup of some holomorphic involution of GLN or a more general group. Okay, so back to kind of the concrete details of our construction in these 3 weak order graphs. So S infinity acts on polynomials in a countable set of commuting variables just by permuting variables in the usual way. And then this lets us define a divided difference operator, partial I, which acts on a polynomial where you take the difference between f and si acting on f, and then you divide by xi minus xi plus 1. So if you haven't seen these operators before, it's always a healthy exercise to note these standard properties that they obey the usual braid relations for the symmetric group, and they square to 0. Okay, so now I'm going to state just a general kind of I don't know, well-known result for these three different cases simultaneously. So let W be either of our kind of sets of permutations. We have three choices. And then let kind of this one indicate just the unique source element in our weak order graph. So this is either going to be the identity permutation or this infinite product of two cycles in the fixed point free case. Then for each choice of W, there's a unique homogeneous family of polynomials that assign this bottom element the value 1, and then satisfy these divide difference relations in terms of the weak order graph. So I can write this as applying partial I to the polynomial indexed by W is summing over vertices V that have an arrow indexed by I that end up at W. So you can get multiplicities in this summation in this event when there are two edges of the form V arrow I to W, but that's only in this orthogonal case. So you have this sort of a very, very general theorem, which I haven't attributed to anybody, but this is almost just like an exercise once you have a construction of those relevant polynomials. But this gives us three different families of polynomials, and I'm going to refer to these as Schubert polynomials in the case when W is S infinity, or as involution Schubert polynomials in the I infinity case, or as fixed point free Schubert polynomials in the remaining case. So here are just some examples of these polynomials, and we see some properties like they have apparently non-negative coefficients. We can see some coefficients that are 2 in the involution case. So let me just say the geometric significance of these families. So if we are still in this GLN case with the Borel subgroup of lower triangular matrices, then we have an isomorphism from the cohomology ring of G mod B with polynomials modulo the ideal lambda plus generated by symmetric elements of positive degree. So in the case when either K is the Borel subgroup B or the orthogonal subgroup, the orthogonal group or the symplectic group when n is even, K acts on G mod B with finitely many orbits. These orbits are in bijection either with Sn, In, or these fixed point free involutions. And if you denote the corresponding closures of these orbits as XW, YW, and ZW, then these three families of Schubert polynomials are exactly just giving you the cohomology classes modulo are ideal. Okay, so this is the reason to be interested in these polynomials. But they have lots of interesting positivity properties. So they're dating back to early 90s, we know that Schubert polynomials have non-negative integer coefficients, and there's various formulas for those coefficients. Schubert polynomials are a basis for all polynomials. We have this famous kind of combinatorial problem of giving a formula for the positive structure coefficients arising when you multiply Schubert polynomials. So concerning these involution and fixed point free involution Schubert polynomials, these are no longer bases of all polynomials, but they are at least linearly independent due to the following result, that there are certain finite sets of permutations such that the involution Schubert polynomial is a power of 2 times this multiplicity-free sum of ordinary Schubert polynomials, and the fixed point free Schubert polynomial is just the multiplicity-free sum. So these sets of permutations can be explicitly generated. So there's a kind of an efficient formula or a sort of equivalence relation that lets you detect all these elements. Another way of characterizing these sets is in terms of the strong Brouwer order. So it can be shown that if you have an involution, then the set of Schubert terms in the involution Schubert polynomial are indexed by the minimal length permutation x with this property that x times w is less than or equal to x. And then a similar property can characterize the elements of this other set. So there's certain interesting explicit characterizations of these elements. Okay, so let's now sort of transition to talking about key polynomials. So there's two different ways of adding fixed points to the beginning of our permutations. So for elements of S infinity, we can just add fixed points in the ordinary way to our permutation, then shift up the one-line notation. So for fixed point free involutions, we have to do something a little bit more involved since we don't want any fixed points. Rather than shifting up our one-line notation and just having 1, 2, 3 up to n, we want to assume n is even and then intersperse these two cycles, 2, 1, 4, 3, up to n minus 1. So we have these two different ways of shifting elements of S infinity, I infinity, and I FBF infinity to the right. So when you do this shifting, you are suddenly adding all these ascents to the beginning of your permutations. And so the way that we define these polynomials as to satisfy these divided difference relations implies that when you do this shifting, you're suddenly going to have symmetry in your first n variables. And so if you do a limiting operation, you kind of do this shift, adding these fixed points or two cycles in the limit, then you'll get well-defined symmetric functions, which we'll talk about a little bit later. So another way of shifting up these three families of polynomials is using isobaric divided difference operators. So these we're going to denote as pi I, and they're just our ordinary partial i's applied to xi times f. And so it's a useful exercise that if you just apply a sequence of these pi i's from 1 to n once, that's going to shift your the index of your Schubert polynomials up by 1. And if you do it n times, you'll shift up by n as long as n is sufficiently large. So so now there are certain interesting product formulas for Schubert polynomials. So the Rotha diagram of a permutation is just these boxes obtained by drawing hooks through the ones in your permutation matrix and taking the complement. On the other hand, we have a familiar Young diagram of an integer partition. And if your permutation has Rotha diagram equal to a Young diagram, then we say W is dominant and it has the Schubert polynomial is just a monomial as a product formula. So similarly, if you have an involution whose diagram restricted to weakly above the diagonal is the same as the diagram of a partition restricted to weakly above the diagonal, then we have a product formula for the involution Schubert polynomial, which is as a product of binomials, xi plus xj. And then we have a totally analogous formula in the fixed point free case when we're just restricting to strictly above the diagonal rather than weakly. So these product formulas are the starting point for a definition of key polynomials. So define kappa lambda q, and kappa lambda p as exactly these product formulas we saw on the previous slide, indexed by some partition. So Schubert polynomials in our three different cases were obtained by applying these ordinary divided difference operators to these product formulas. And the idea for key polynomials is instead of applying ordinary divided differences, you apply these degree-preserving pi i's instead. So the definition that we'll use is just a key polynomial in the classical sense is just any polynomial obtained by starting at kappa lambda and applying a sequences of isobaric divided difference operators. And then we have p key and q key polynomials obtained in a similar way, but from a different starting point. So this is our kind of algebraic definition. So you can index these objects by families of compositions. Compositions meaning just sequences of non-negative integers with finite sum. So the idea is that when your composition is a partition, so it's weakly decreasing, we have these product formulas as a base case. And then when you apply a single isobaric divided difference operator, you're either going to swap decreasing parts of your composition or you're going to fix your polynomial. So for these three different families of key polynomials, you have these familiar recurrence relations. For our new family of shifted key polynomials, the natural index set are not arbitrary compositions, but ones that are symmetric, where a symmetric composition is going to be one that sorts to a self-conjugate partition. So some positivity properties of these polynomials. So there's many interesting positive formula for key polynomials, combinatorial formulas. And then we can show that each of these p key and q key polynomials is key positive. So it's a linear combination of key polynomials. So it will also be monomial positive. So one thing that we don't really have a good understanding of is what precisely the monomials or key terms that appear in these expansions are. So in contrast, say, to the Schubert polynomials, where for an involution and fixed point free Schubert polynomial, we can really generate the Schubert terms in an explicit sense. So here we don't have a way of constructing things in a fast way. But so the type of key expansions you get kind of look like this. So these summations. So in the Q case, there are powers of 2 that appear at the front. So let me say about where our naming conventions come from. So suppose you have a partition with at most n non-zero parts. So if you just reverse this partition, then you get a composition that is weakly increasing. And so it is fixed by the first consecutive isobaric divide differences, which means it's symmetric in these variables. And in fact, in this setup, so the key polynomial of this reverse partition is just a Schur polynomial in n variables. So similarly, if you take a self-conjugate partition, then the p key polynomial of its reverse is going to be a certain Schur p polynomial, and the q key polynomial of the reverse of this partition will be a certain Schur q polynomial. And here, the indices of p mu and p and q nu are just the strict partitions that give the row counts of lambda either weakly above, strictly above, or weakly above the diagonal. So very brief review. So Schur functions, Schur p functions, Schur q functions are these 3 kind of parallel families of symmetric functions. So Schur functions are just going to be generating functions of semi-standard tableau, whereas Schur p and Schur q functions are generating functions for semi-standard shifted tableau. The only difference between p and q is that in our generating function for p, we don't allow primes on the diagonal of our shifted tableau, which means that the q polynomials are a power of 2 times the p ones. And each of these families is a basis for a ring with positive integral structure constants, and there's other ways to kind of motivate the consideration of these particular functions. But the takeaway is that these 3 families of key polynomials are in some sense non-symmetric generalizations of these 3 families of symmetric functions. So like Schubert polynomials, key polynomials are a basis for all polynomials. So unlike the linearly independent sense of involution and fixed point free involution Schubert polynomials, our p key and q key polynomials actually exhibit some non-trivial linear dependences. So the most interesting result of this type is that each Schubert polynomial is key positive, so a linear combination of key polynomials. And then we conjecture, which is sort of the motivation for considering these p key and q key polynomials, is that our fixed point free Schubert polynomials are p key positive and our involution Schubert polynomials are q key positive. So more specifically, our conjecture is a little more detailed. We expect that there is a specific set of symmetric compositions so that you have these particular expansions of these Schubert polynomials. So we have some examples like this. So we've tested this as much as we can. And then there's even some stranger examples that we'll talk about slightly in a second, where you can actually have 2 different expansions of the same involution Schubert polynomial into Q keys. So one application of these conjectures, so we again return to these symmetric functions that are adding fixed points to the beginning of our permutation and then taking a limit. So in the original Schubert case, so this limit is always going to be a Schur positive symmetric function, and this was shown in a bijective way by Edelman and Green. So this would also follow immediately from the key positivity of Schubert polynomials, because if we just applied this sequence of isobaric divide difference operators, on the one hand, it'll add fixed points to the beginning of the index of SW, but on the other hand, it will also sort and reverse the index alpha in your key polynomial, turning it into a Schur polynomial. So if you apply this divide difference operator on both sides, then you'll just get an expansion of your limiting Schubert polynomial as a sum of Schur terms. So similarly, if you take these limits of these power series of given by adding fixed points at the beginning of a fixed point free or involution Schubert polynomial, then the result are Schur p positive and Schur q positive symmetric functions. So this is shown in a different algebraic way in the literature, but it would also be an immediate consequence of this conjectural p key and q key positivity. So I'll just a few more other results sort of motivate these shifted key polynomials as interesting definitions. So there's a simple scalar relationship between Schur p and Schur q functions, and a similar phenomenon occurs for these p key and q key polynomials. That in certain cases, one is a power of 2 times the other, but this is more limited than in the general relationship between p lambda and q lambda. And then one other interesting conjecture. So it's known exactly when a Schubert polynomial is equal to a key polynomial. And that is precisely when you're dealing with a permutation that's 2, 1, 4, 3 avoiding. And the composition index alpha is just equal to the code of your permutation. And then conjecturally, this exact same classification restricted to involutions tells you which involution Schubert polynomials are equal to Q key polynomials. And then finally, just to conclude, so the higher level kind of idea of proving these conjectures. So Asaf Schilling identified certain connected crystals whose characters give Schubert polynomials and key polynomials. And then they showed that there's actually this identity that expands Schuberts into keys lifts to a crystal isomorphism. And so we constructed analogous crystals of a different type whose characters give these different families of fixed point free involution Schubert polynomials or p key and q key polynomials. And we expect that these positivity conjectures actually lift to isomorphism between the relevant crystals. And I showed earlier that there was at least one involution Schubert polynomial with multiple q key expansions. But actually at the crystal level, there's only one crystal isomorphism. So sort of one of these expansions is sort of bogus and doesn't apply to the crystal setting. So maybe there's hope there's really a canonical kind of expansion going on. And then also, I'll just say that there are some K-theoretic analogs of key polynomials and p key polynomials, but it's an open problem to kind of describe something that similarly works in the q key case. All right, so thanks. I'll stop there.